Hello. So my name is Keith Zbudzinski, and I'll be going over our CS230 final project. For this project, we created a 2D food simulation. So now I'm going to go over the basic architecture of our project. Essentially, we can split it into two different components, the simulator itself and the renderer that creates the visualization of that simulation. So for the simulator, we used the Eulerian methodology. Essentially, this means splitting the fluid into a grid of cells and running the simulation on that discretization of space, as opposed to tracking the velocities of the particles in the fluid themselves. To do this, we used the marker and cell grid. Essentially, what this does is it splits all the values of the velocities and pressures into separate grids. So we actually have three different grids that we combine together to simulate our fluid. Each grid cell can be scaled to be the desired length. You can just use a scalar in the different equations throughout the simulation. We just left ours to be units, so we just left them to be a unit of one. The staggered grids um, like I said before, we have three different grids for the different values we'll be using. We have a grid for the horizontal velocities and a grid for the vertical velocities. And of course, we can combine those together to get the actual velocity of each grid cell. And then we also have a grid for the pressure values of each cell in our simulation. This setup is highly recommended because it allows for a much simpler pressure calculation later on in the simulation. We can kind of give an overview of what a simulator does by these three steps down here at the bottom. So first, it will compute the body forces that are applied to the liquid. For us, this just means gravity. And then it will calculate and apply the pressure to the fluid. And then it will advect the velocity vectors in the velocity field that the simulator computes. Advecting velocities is essentially just tantamount to updating the velocity field itself. And so just in summary, the simulator, its output is a velocity field for every frame that we want to simulate. So it's going to output a whole list of uh, velocity vector fields. Um, we can use the output of the simulator to actually render what we've simulated. So like I said, the simulator outputs a lot of velocity fields. We output those to a text file. Um, we ended up using Unity for our renderer just because we had already a little bit of experience with that, and there were a lot of options for rendering this stuff, but we didn't need to go ahead and have to learn one of those, so we just opted to use something we already knew. We import into Unity the velocity fields that the simulator outputs. We import them as a list of matrices. Um, and then we can see here on the right, this is kind of what our Unity scene looks like. This white box is the camera, and then all these black circles are particles that we place randomly into our velocity field so that we can visualize what the velocity field is actually doing. Essentially, for every velocity field that we have, and by velocity field, that kind of means like frame. So for every frame we want to render, we iterate through all of these particles, and depending on where they are within that velocity field, so we just get their x and y locations and apply it to the velocity field, we update their velocity with that of what they have in the velocity field itself. But we'll visualize this later on. You'll yeah. So in our pre-proposal, we had a few goals that we wanted to meet for this project. We can just kind of quickly go through them and see what it took to implement. So these are our six goals. Let's go through them. So first, we needed to determine a time step. As we were initially starting out on this project, this seemed like a very important step. It seemed like if we didn't get this quite right, we would either have a really awful simulation or it would just take forever and never finish. So essentially what we did early on was we just kind of used a small placeholder, and then we were planning after we had finished the simulation or simulator to go back and implement one of the many methods that exist to create an accurate time step. However, we found that we were getting pretty good results just by using this constant, and so we didn't actually bother to um, mess with it and delve any further. So like I said, we apply gravity in our simulation. This is actually a pretty straightforward step. We have the velocities to which we need to apply gravity. We have a time step in units of seconds. We also know the acceleration due to gravity in meters per second squared, right? Just 9.81 meters per second squared. That's an approximation, but close enough. That's what we use. So if we multiply the time step and the acceleration, right, we have seconds times meters over second squared. We can cancel out the seconds, so we get meters per second, which is just velocity. So we can just subtract this value from the current vertical velocity we already have. So for every vertical velocity we have in our fluid, we can just subtract this quantity from it, and that applies gravity. Now we can apply pressure itself. This is kind of the heart of the fluid simulation. If we apply pressure correctly, then we can enforce the incompressibility and boundary conditions that we want for our fluid. This equation right here is how we would actually go about applying the pressure. We have all these quantities except for this. This is the vector field that we want to compute at the next time step. This is our current vector field. This is our time step. This is 1 over the density. We just used our density equal to 1. And then this is the gradient of the pressures. So this is what we need to figure out how to get. And we can get this by solving this system of linear equations where A is a matrix of uh, coefficients, P is what we want to solve for, and B, this right-hand side, is actually the negative um, negative divergences of all the fluid cells in our simulation. So there's many ways to solve large systems of equations like this. We ended up using the Gauss-Seidel method. It's an iterative method. It's good for simple simulations, and it's easier to implement than the conjugate gradient method. So this is why we opted for this instead of the conjugate gradient method. As I said, it's iterative, so you're supposed to do it over many times and eventually it converges to a solution. However, when we implemented it, we found that ours was never converging. So we tried that out just with one iteration, and it actually gave good results. So we just went with it. Applying boundary conditions is actually part of the pressure step. Essentially, it amounts to just setting all the pressures along the edges of the simulation to 0. And that kind of it makes the simulation look as though there are walls around um, the edges. And then we needed to add vector velocity. Like I said, add vector velocity is essentially just updating the velocity field in the correct manner. So basically what it does is you take a cell inside the current velocity field and you project backwards to figure out what particle that is currently in that cell, where it would have come from. And then where that particle would have come from, you take the velocity value there and stick it at the current cell. So that's kind of what I'm saying here. And this equation is how you figure out where a particle comes from. So this is your current cell location, this is the time step, and this is the velocity at your current cell location. And that would give you some location inside your vector field. Of course, this location is not guaranteed to be aligned with the grid cells, and so some interpolation is required. We used simple forward Euler, and it seemed to work well enough for us. And so, of course, we were able to render our simulations, and I'll just walk through a few of them. So this one is with gravity. As you can see, the particles swirl around on this left-hand side. They do act as though there's a wall. We had some difficulty with the other sides, and accident indices, but we do know it works at least on this left side. I skipped one. All right. And so the reason why I'm showing some with gravity and some without gravity is because we actually felt that those without gravity looked more realistic than those with gravity, which is a little bit counterintuitive, but there you go. And the last one. So we were able to set up these simulations just by specifying different horizontal, vertical, and pressure values in our initialization of those grids for the simulator. And that is our presentation. Thank you very much for listening, and